students. Welcome to the EN 401 lecture on beam analysis, reaction forces. Here's the roadmap for this lecture. We'll do some terminology, then we'll look at beam loadings, beam reactions, and static equilibrium. This lecture is going to focus on beams, which beams are horizontal structural members that are designed to carry building loads over to columns. So some other names you might have seen for beams are here: girder, purlin, joist, rafter, or stringer. A beam that is holding a load on a building. This may seem silly, but a beam that's holding the load is in static equilibrium, right? It's not moving. We don't want it to move. That's not a good state for a building to be moving. So all our beams are in static equilibrium, which we've seen that analysis before in this class. And all beams are essentially connected to a column, and that column provides what we call reaction forces. So that's the focus of this class here, is to calculate reaction forces where beams are connected to columns. There may also be a reaction moment where the connection's at, depending on the type of connection. So here's our pictures here. So in this bridge picture, we have some large beams, right? So these beams will carry the load from the cars and trucks that are above when this bridge ends up being built. And those loads will be carried over here to actually another beam, right? There's a beam across here. And then this beam will carry this down to this column here. And then this column will carry that load into the foundation system, which carries it into the ground. So beams carry the building loads essentially over to the columns, and the columns carry those down into the foundation. So beams are all connected, again, to some type of column or maybe another beam, but it doesn't really make a difference because we make assumptions about those types of connections in one of three ways. We can say that those connections are one of three different types. The first one is a fixed connection. That's modeled by this symbol right here, this straight line with these angled lines. So a fixed connection means that the connection is designed to resist any type of movement, right? So any type of lateral movement or rotation. So you could think of maybe a heavily bolted connection or a welded connection, something where there's no ability for the beam to move from its connection. In a fixed connection, you see that we have three different reaction forces. We have a reaction force in the y direction. So that means our column is keeping this beam from falling straight down. We have a reaction force in the x direction, which means that the column or the connection is keeping this beam from moving or accelerating laterally, left or right. And then this is probably the most difficult concept to understand in this lecture is the reaction moment. So that means we have this reaction moment here at our fixed connection, which means that it's not allowing for rotational acceleration of our beam. So just to do a quick sketch for you guys. So if we had a beam here like this, right, that reaction moment is keeping this beam from falling and rotating like that. All right. So next we have the pinned connection. So pin connection over here. So our pin connection resists forces in all directions, but does not resist the moment, right? So we resist an x and a y force, but not a moment. So if we had, let's just say we had a beam that's this one's sticking up like this, right? If we put that beam like that, it could very easily rotate that way or that way, but it wouldn't be able to move left or right. So over here in the fixed, it can't rotate, but on the pinned, it can. And a good example of a pinned connection is your door hinge, right? You can't rip the door off the wall, so it's resisting, the hinge is resisting x and y forces, but the hinge doesn't resist moment, which allows you to open and close the door. All right, and then our final connection is a roller connection. Roller connections only resist one force. So in this configuration, we sort of have a fixed thing right here. So this roller here would only resist a force in the y direction. So if we had a beam here, right, the beam beam can't go down, right? But, if we pushed on it that way, the beam would roll. And also, if there was nothing over here on this end, then this beam could also just rotate freely that way. So a roller only resists one force, and typically that's going to be a y direction force. Here's some pictures of those different types of connections. So here's our fixed connection right here. We can see that we've got our beam here, and we've got another beam here, and we've got a column here, and we get this nice heavy bolted connection here. So these connections are resisting, a y force, right? So the beams don't fall down. Resisting an x force, right? So they can't be moved laterally, and also resisting that moment, right? So if there is, let's say this beam was just that long, right? If the beam was only this length here, and there was nothing on this other end, this beam wouldn't just rotate down like this, right? It would be held steadily in place, and that's how we know we have a reaction moment there. Here's a good pinned connection, right? So this column here, we get a column on this one. This column here is pinned to the foundation system, right? So it can resist these lateral forces, right? So the thing's not going to just come flying off. Obviously, the foundation is resisting a y direction force, keeping it from just sinking into the ground. But we see we got this big bolt here. So this connection does allow this to rotate this way or that way. Depends on the structure. Maybe the structure is fixing it higher up, but at the connection here, this can rotate. This is a great type of connection when you're doing steel structures, because it allows you to connect it to the foundation and then lift that piece up. So you can connect it while in a laying down state, and then you can lift it up and then connect other pieces to it. Here's another example of a pin connection right here. You can see that if this was cut here, this would just rotate down this way, right? So no reaction moment on our pin. And then here's a roller connection. Got a nice roller connection here. So this big roller here is keeping this giant beam up, but this beam is free to move that way or that way. And if this were to be cut here, you could tell this would just rotate over this way. There's nothing keeping it from rotating. So our roller only has that one reaction force. All right, so now that we know what reactions are, we can talk about how beams are loaded. So beams are typically loaded from above. I think that's makes pretty good sense there. And they have to resist the weight of the objects that are placed on top of them, right? If they don't resist those objects that are placed on top of them, the beams will fail. That's not a good building to be in. You don't want your beams not resisting those loads. So what are the types of loads we can put on beams? Some civil engineering terminology. We have what's called the dead load or live load, snow loads, earthquake loads, wind loads, all types of loads. But the basis of those, we end up showing those loads as force vectors, so we can do our analysis. So we'll kind of go through these different types of loads that we could apply. So we'll start with the easiest one here, a point load. All right, point load. We've seen those before in statics. So that's just a load applied at a single point in space. So this has a magnitude, in the y direction only, right? And has a direction in the y direction, and the magnitude will be shown. So that's kind of an easy one. We also have our angled point loads. So this has a x and y component, right? So you should already remember how to resolve that angled load into its x and y components. So that's something you'll have to do when you do your analysis for the reaction forces. And then getting into our more complicated loads, we have what's called distributed loads, right? So this is a load that's applied over a distance. So good examples of distributed loads might be flooring material, right? So you put flooring material over the entire area that you're working or that you're building, right? And so we would model that each tile has a certain weight, right, and a certain size. So we knowing the weight and size of those tiles, we say, okay, well, this particular tile, by applying to the floor, is going to apply a distributed load of X magnitude over the length of the floor. So yeah, we'd model those as distributed loads. So distributed loads have units of force per length, right? So pounds per foot, potentially. And so for distributed loads, what we have to do our reaction analysis is to calculate what the total load is, and then where that total load acts, which is at the centroid of the distributed load shape. So for this rectangular one, this is a pretty easy one to find the total load for and the location. So location's easy, right? That's at the centroid, so that would be there. And the total load would just be the area under this distributed load shape, right? So it would be the magnitude of the distributed load times its length, right? Length cancels, you're left with just the force, right? So our equivalent load would be this force here at the center of that shape. If you had to do the equivalent load for this this more complex one here, you could break this into two shapes, and you could even model this as two forces: the distributed load from this rectangular piece and the distributed load from this triangular piece, right? So this one would act there, and that one would act there. Or you could find the centroid of this whole thing and the area under this entire curve and model this as one point load for your reaction analysis. So here are the steps to find the reaction forces for our beams. If not already done for you, step one, label all of your unknown reaction forces. So we like to give each connection a name, probably an alphabetical name, A or B. So A means at connection A, you have a reaction in the X, a reaction in the Y, a reaction moment. Maybe there's a B and you have just a reaction in the Y on the B. So just figure out what type of connection you have and then label those unknown forces or moments depending on the type of connection. Second step, resolve all those distributed loads to a single point load. That way you can do your static equilibrium analysis. If there's any dimensions you think you need, go ahead and label those out. And then go ahead, make sure that you don't have any more than three unknowns, right? Remember, 2D static equilibrium, we can only have three unknowns and three equations. And here are our three equations: some forces X, some forces Y, and some moments about an arbitrary point, all equal to 0. So good practice on these. I like to try to just pick the leftmost reaction for my sum moments equation, because by doing that, it zeroes out the distances of any force there. So that usually lets me solve for one of my unknown reaction forces. If you have a fixed connection, right, fixed connection has three unknowns. So you're not going to have, if you have a fixed connection, you probably won't see multiple connections on your beam. So if it's just fixed, you have three unknowns, so that's all you can really solve for. So when you do your moment equation for a fixed connection, always pick the fixed end, and that will allow you to solve for your reaction moment at the fixed end. And then remember to use that perpendicular distance, right? So if you have, a fixed connection here, and you have an X force at the end of the beam, right? Remember that perpendicular distance is 0 from this fixed connection here, because it's on the line of action. If you had a Y force, then this would be your perpendicular distance. So as a reminder from the early slides in this presentation, a beam that is successfully holding the load and not failing is in static equilibrium. And as we know, static equilibrium is achieved when there are no net forces or moments acting on the system, or in this case, the beam. All right, that means that sum of forces are equal to 0, and we're doing 2D problems, so that's in the x and y direction. And sum of moments about any arbitrary point equal to 0, and those moments are about the z-axis. And that z-axis, in this case, would be the one that's perpendicular to your computer monitor. So looking at beams, let's go through and see what that actually looks like. So here we have what's called a cantilevered beam. It's cantilevered because it is fixed on this left end here. So if you have a beam that has a fixed connection and is free on the other end, we call that a cantilevered beam. So we got our cantilevered beam here. Let's say we add a load at the end of our cantilever beam in the x direction. Well, to keep this in static equilibrium, we know that we need to have a reaction force in the x direction to keep this from moving. We add a load in the y direction to the end of the beam, or any spot on the beam. We'll just say the end in this case. We need to have a reaction force also in the y direction to make sure that this cantilever beam isn't just going to fall straight down. And so this may, to some people, look like it's in static equilibrium, but we know that it's not, right? Because the combination of our reaction y force and our y direction load is going to cause rotation in this direction, right? If we just put those forces on there, it'll rotate this way. And so to combat that, our fixed connection also is going to provide a reaction moment about the z-axis. That way, this cantilever beam does not experience any kind of rotational acceleration because of the loading, right? So on our fixed connection here, remember we have a reaction force in the y, a reaction force in the x, and then this reaction moment about the z-axis to keep this thing from rotating that way. All right, here's example 1a. So there's another video to solve this, but we can go through it on this PowerPoint. So we have a beam with a pin at point A and a roller at point B. So we call this simply supported. If you have a pin on one end and a roller on the other, so let's say simply supported beam with a 7,000-pound load right in the middle. All right, so we'll quickly go through this. So we need to define our unknown reactions, so AX and AY at the pin, and just a BY at the roller. Looks like we have everything we need to now solve for our three unknowns. So we just need our three equations. First equation, sum forces x equal to 0, and the only thing we have in the x direction is AX, so AX is going to equal to 0. Second equation, sum forces y equals to 0, so AY plus BY minus 7,000 pounds is going to equal to 0, and we can deduce from that that AY equals 7,000 pounds minus BY. And then our third equation is going to be our moment equation. So we'll do some moments at point A equal to 0. Remember, we take our forces times the perpendicular distance from A and just analyze all of those. So we have our negative 7,000 pounds times 5 feet away, plus our 10 feet times BY, and that all equals to 0, right? AX and AY are excluded from the equation because their distance from point A is 0. They're technically at point A. All right, so solving for that in that sum moments equation, we can get that 35,000 foot-pounds is equal to 10 feet times BY, and therefore BY is 3,500 pounds. Plug that back into our sum forces y equation, and AY also equals to 3,500 pounds, which should not be too surprising. We got 7,000 pounds in the middle of this beam, so half should go to either side. All right, example 1b is kind of a different take on example 1a. So we have that same simply supported beam. It's 10 feet long, but instead of having a 7,000 pound point load in the middle, we have a 700 pound per foot distributed load. All right, so the process is still about the same, except what we have to do in this one is we need to resolve our distributed load to a single point load. So we got to find the area under the curve of this distributed load here. So this is just a rectangle. So our area under the curve will be 700 pounds per foot times this 10 feet, right? And so that'll equal 7,000 pounds, and that acts at the centroid of our distributed load shape here, so that'll be right in the middle. So that's what we would now do our static analysis with this point load here of 7,000 pounds, which we just did in example 1A, so we should end up with the same reaction forces. All right, example 2, go ahead and watch the video for example 2. And example 3, go ahead and watch that video for example 3. Note that we have a fixed connection at point A, and therefore you'll have a reaction moment. All right, here's your review. So beams are horizontal structural members, and they carry building loads over to the columns, right? Beams carry the building loads over to columns. They might carry it to another beam, which will eventually carry it to a column, but they all end up at the columns. Our three types of beam connections are fixed, pin, and roller. Remember, at a fixed connection, we have a reaction force in the X direction, a reaction force in the Y direction, and a reaction moment. That's our fixed. Our pin only resists forces in the X and Y direction, and our roller resists only one force, typically in the Y direction. How do we just resolve distributed loads? We find the area under the curve of the distributed load. That's the magnitude of the equivalent point load, and the location of that point load would be at the centroid of that area under the curve shape of your distributed load. So if it's a rectangle, we're at right in the middle of the distributed load. If it's a triangle, it's a third from the big end. And then how do we calculate reactions at beam connections? We do our static equilibrium analysis, just making sure that we label all of our unknown reaction forces based on the connection type. All right, that's it for this lecture. Thanks for watching.